Good afternoon, everyone. Today we're going to do a video on graphing the tan function and going into details of where we get the important points on the graph. And so if we look at the function y is equal to tan of x, we know that tan of x is really the rational function sine of x over cos of x. Okay? And so if we want to start by finding the zeros of our tan function, then all we're really looking for is when this fraction, this sine x over cos x, is equal to 0. Now, we know that for a fraction to be equal to 0, we simply need the numerator to be equal to 0. As long as the denominator isn't also equal to 0, in which case we would have an indeterminate form, but that's never the case here because sine x and cos x are never both 0 at the same time. And so we won't run into that sticky situation. All we have to consider for our zeros is when is sine of x equal 0, right? Because our numerator being 0 makes our entire thing equal to 0, right? 0 over anything is always equal to 0. And so all we have to solve is sine of x equals 0, okay? Now, that means that x is equal to the sine inverse of 0, and those give us the solutions 0 or pi or 2 pi or 3 pi, and so on and so forth. Or if you'd rather, 2 pi times k, where k is any integer, right? And so if we go ahead, and there's a reason for this, I'm gonna put pi, I'm gonna put 2 pi, and then similarly negative pi, negative 2 pi. That means that we know we get zeros at every integer multiple of pi. At 0 and every integer multiple of pi, even into the negatives. And so we can plot those points as such, okay? Now, the other important points to look at are going to be our vertical asymptotes. And if you've seen a graph with tan of x before, you've seen those dotted hash marks with vertical asymptotes vertically down the graph, okay? Now, those occur at any point of a function where the denominator is equal to 0. Because the denominator equal to 0 is a faux pas in mathematics. It means our function is undefined, okay? So if we're looking for points where tan of x is undefined, all we're really looking for is when its denominator, namely cos of x, is undefined. Or, I should say, when cos of x is equal to 0, so that the function is undefined, because the denominator is 0, okay? So, now we're thinking of the equation cos of x is equal to 0. And if we wish to solve that, we can take the inverse cos, so x is equal to the inverse cos of 0. And so, now the inverse cos of 0, I'll remind you of a unit circle. Our unit circle, cos of x, or should I say cos of theta, is the x coordinate, right? So when is the x coordinate on the unit circle 0? Well, it's not here. Here the x coordinate is 1. Here we have the point 1, 0. But if we go up here, where the point is 0, 1. So here the x coordinate is 0, and so cos of theta is 0, okay? And then likewise at the bottom here, where it's 0, negative 1, and so the x coordinate is 0, so cos of theta is 0. And so our two solutions within one revolution of the unit circle for the inverse cos of 0 is we are here at pi over 2, always measuring from the positive x-axis, so pi over 2. And at the bottom, we're at 3 pi over 2, right? And we can also consider the negative values of pi, and so we could also write 3 pi over 2 as negative pi over 2. If we drop down by pi over 2 from the positive x-axis, we would get negative pi over 2. And so in that case, we can write all of our solutions as pi over 2. And then from this point, we're looking at any integer multiple of pi. So plus 1 pi brings us here, plus 2 pi would bring us all around, plus 3 pi would bring us down here, plus 4 pi would bring us all around twice, and so on and so forth. And so our solutions for x equal to the inverse cos of 0 are pi over 2 plus or minus, excuse me, plus or minus pi times k, okay? Where k is any element of the set of integers. Because again, any k multiple of pi, remember pi is only half a circle, so any k multiple of pi brings us to solutions where cos of theta is equal to 0. And so here are our solutions for cos of x is equal to 0. And so that means that we have our first vertical asymptote at pi over 2, right? Because cos of x being 0 means that our denominator is equal to 0. Okay, so let's actually take the time to write that out. This is going to provide us our vertical asymptotes. And so our first one will be at pi over 2. And so pi over 2, and then we'll have 3 pi over 2. And then the negatives, negative pi over 2. And likewise, negative 3 pi over 2. We're going to get our first vertical asymptote at x is equal to pi over 2. And so we have a nice dashed line all the way down. And then at every k multiple of pi, and so 1 pi later, we're at 3 pi over 2. 1 pi backwards, we're at negative pi over 2. Another pi backwards, we're at negative 3 pi over 2, and so on and so forth. And you might notice that if we plot our zeros and our vertical asymptotes, I actually forgot one solution. One of the zeros is at the origin at x equals 0. So between every two vertical asymptotes, we have a 0. Between every two vertical asymptotes, we have a 0. Every two vertical asymptotes, we have a 0. And that's not by coincidence, not by chance. That's exactly how our tan function works, in the sense that much like sine and cos, our tan function is periodic, okay? And it's periodic about every set of vertical asymptotes. And so now, if we want to sketch it, every period of the tan function looks like so. So it goes from positive infinity to negative infinity, or negative infinity if you'd rather, up to 0, through to positive infinity. Okay? And it continues that way forever and ever. And the last piece of information that can be relevant is you might wonder, well, it's periodic with what period? Well, it's periodic with the period that is the distance between each successive vertical asymptote. And so what is the distance between every consecutive vertical asymptote? Well, it's exactly 1 multiple of pi, right? So that's pi apart. This is pi apart. This is pi apart. And so we have a period. Wow, that is not how we spell period. Excuse me. Period of pi. Okay? And so this is our very general y is equal to tan of x function graphed. We have our zeros on the x-axis at every integer multiple of pi, negative 2 pi, negative 1 pi, 0 pi, 1 pi, 2 pi, and so on and so forth. We have our vertical asymptotes at pi over 2, plus or minus any integer multiple of pi, so pi over 2 plus 1 pi, plus 2 pi, plus 3 pi, pi over 2 minus pi, minus 2 pi, minus 3 pi, so on and so forth. And every two vertical asymptotes are separated by pi units. And so the tan function is periodic with a period of pi, because every cycle happens every pi units along the x-axis, okay? I hope that gives you a bit of a visual framework of how the tan function looks very generally, of what the baseline of the tan function looks, before we get into the transformations and how to kind of deal with those details in a graph, okay? I hope this helps. If you have any suggestions for future videos, please let me know. Any comments, improvement suggestions are always appreciated. And thanks for watching.